is when it switches, the microphone unmutes again.
Okay. Okay, so welcome everyone to the final talk of this session. So the speaker for this talk is Dr. Subhrakanti Day. So Dr. Day is a professor with the Hamilton Institute of National University of Ireland in Maynooth, and he's also affiliated with the Department of Engineering Sciences in Uppsala University in Sweden. So prior to this, he was a professor with the Department of Electrical and Electronic Engineering in the University of Melbourne, Australia, for nearly 13 years. He received his PhD from the Department of Systems Engineering at Australian National University, and he has held postdoc positions in the same university as well as at the University of Maryland in College Park. So he has a wide area of research interests, including wireless communication and networks, signal processing for sensor networks, network control systems, and molecular communication systems. He has served on the editorial board for numerous journals, including the IEEE Control Systems Letters, IEEE Transactions on Control of Network Systems, IEEE Transaction on Wireless Communications, IEEE Signal Processing, and IEEE Transactions on Automatic Control. So today he's going to talk about how can we transmit data over a lossy channel for remote estimation purposes when an eavesdropper is present over the channel. So Dr. Day, it's a very pleasure to have you at ISC, and the floor is all yours.
Thank you very much, Vaibhav, and thank you for the invitation. So without further delay, I will get into the actual talk. The title of this talk is Remote Estimation over Lossy Channels in the Presence of an Eavesdropper. And it's a joint work with my longtime collaborators, Alex Leong and Daniel Quevedo, and Daniel Dawes, who was a visiting student in Daniel Quevedo's department at that time. So I'm affiliated with Maynooth University and also with Uppsala University. So the outline, I'll give you a little bit of an introduction about security in control systems and defense mechanisms that one can propose. And you would have already heard a fair bit of this in Kale's talk just a little while ago. So I'll go more quickly into the details of problem setup and preliminaries. And then we'll see that if we have an eavesdropper, basically a passive eavesdropper, trying to decode the data that a sensor is sending and estimate the state of the system, what can we do to prevent a good estimation at the eavesdropper's facility? So first we will do this with knowledge of eavesdropper's channel. And of course, while that is not always possible, perhaps impractical, it will give us a benchmark to compare the situation when we don't have the knowledge of the eavesdropper's channel. So look at essentially what are the kind of optimal transmission scheduling policies that one can come up with, and how one can obtain this optimal transmission scheduling policy. And we'll find that, interestingly, there are some structural properties of this optimal transmission scheduling that makes it easier to implement. And in particular, there are some threshold type policies that one can come up with. And there will be also an infinite horizon, in the infinite horizon scenario, where you are trying to minimize a long-term average cost over an infinite time horizon. We will show that by cleverly designing the transmission policy at the sensor, you can actually make the eavesdropper error covariance on average go unbounded, whereas at the sensor's estimator, it remains bounded. Okay? And we'll show some numerical studies and also an alternative information theoretic measure of security, how that can be applied in this setting. So we have already seen examples of the cyber physical systems where there is a tight integration of communication, control, and computing. And due to the system being exposed to through the internet or through wireless networks, essentially we are vulnerable to security breaches and privacy breaches, as we have already discussed in the previous talk. So I am more interested in specifically network control systems, where essentially you have a system which could be an automatic control system or a plant that has sensors and actuators. The sensors send their measurements or some information over a wireless network to a remote controller. Remote controller also sends decisions or actions through a wireless network to the actuators. So both these links could be vulnerable to attacks. And so the types of attacks that you can have are of many types. One of them is called the active attacks. You can classify them as active or passive attacks. In active attacks, you can have data integrity attacks or false data injection, replay attacks, and so on, or denial of service attacks, where the actual resources for the control system are being denied. So, for example, the communication channel between the sensor and the remote controller can be jammed by the attacker. In this talk, we will look more at passive attacks, which is sort of what we call as eavesdropping. And already in the previous talk, you would have heard about how simply encryption-based security may not always be enough, because sometimes we can have authenticated users also causing attacks into the system. So I won't go into the details and examples of this. They can be found in the relevant papers. So we'll focus on eavesdropping. And here I will very quickly talk about information theoretic security, which of those of you who are familiar with this concept of a three-terminal scenario, where you have Alice who wants to transmit to Bob, but wants to also make sure that the eavesdropper Eve cannot decode Alice's data. Now, most of this information theoretic security relies on mutual information between Alice and Bob, maximizing the mutual information between Alice and Bob, while trying to minimize the mutual information between Alice and Eve. So that's the type of information theoretic security that has been studied quite extensively, but that's in the context of information transmission, whereas we will be looking at more in the context of control systems and estimation theory. The current work that I'll be talking about today is in the context of state estimation of dynamical systems in the presence of an eavesdropper. So let's go into the system model. So this is perhaps the most important slide of the talk. So we have a process, a dynamical system that is modeled by this process, and the state of the system is given by xk. There is a sensor which can measure the state of the process, perhaps with some noise yk. So here we take a linear state space system model. Now we also assume that the sensor is a smart sensor, and it can actually run a local Kalman filter to compute local state estimates. So those state estimates, the predicted and filtered ones, and their corresponding error covariances are given by these definitions, the conditional mean and the conditional variances. So what's happening here is that the sensor, that it sends the local estimate over a packet dropping channel to the remote estimator. And the packet dropping channel is modeled by this Bernoulli process gamma k. When gamma k is 1, this state estimate is received. When gamma k is 0, the estimator is randomly lost with certain probability. Similarly, gamma ek is the one to the eavesdropper. So it similarly has a lossy channel. Both the remote estimator and the eavesdropper have producing their corresponding estimates and the corresponding error covariances. And we assume the availability of a feedback channel between the remote estimator and the sensor, where the remote estimator computes the optimal scheduling decision as to when the sensor should transmit its data. And that decision is denoted by nu k. So nu k is, when nu k is 0, you don't transmit, and when nu k is 1, you transmit. So this decision is computed the remote estimator and fed back to the sensor. We don't make any assumption about whether this feedback can be eavesdropped also by the eavesdropper. In fact, even if that was the case, we can still show that the results in our paper hold. Okay, so in typical linear state estimation, we generally assume this controllability observability condition. What that means is that the local Kalman filter achieves the steady state error covariance asymptotically. So we will assume that the local sensor had been running this filter for a while, so it has achieved the steady state. So what does that mean? We have already talked about the Bernoulli packet drop model. So gamma k is the model for the remote estimator channel, and gamma k, ek is the one for the eavesdropper channel. And the probability that the packet arrives for the remote estimator is lambda, and similarly, probability the packet arrives for the the eavesdropper is lambda e. So these are the corresponding estimates at the remote estimator and its error covariances. So this is the filtered estimate, predicted estimate, filtered error covariance, and prediction error covariance, similarly for the eavesdropper. And the information set at the remote estimator is essentially the remote estimator knows the scheduling decisions and when the packets have been lost or received, and when the packet the data was scheduled to transmit, packet was not lost, it gets the estimate. So what we see here is that when it receives the transmission was scheduled and the packet arrived, it gets the estimate. And when it doesn't get that, then it simply propagates in open loop. So that would mean that's the same scenario for the eavesdropper as well. And the error covariance then essentially switches back to the steady state error covariance at the transmitter whenever a packet is received and transmission was scheduled. Otherwise, it propagates in open loop as a function f of the previous error covariance, which is given by ax z transpose plus q. So many of the results that type of results that we present today are going to be interesting for the case when A is unstable. So what that means is that when packets are lost consecutively, as you can see for unstable A, this quantity will start growing exponentially fast. And if you lose a lot of packets in succession, then you're going to have a very large error covariance. So first we look at how to design the transmission decision at the sensor depending on if you knew the error covariances at the remote estimator, as well as at the eavesdropper. Okay. Now we know that the sensor may not know the eavesdropper error variance, but this will, even though this is impractical, this will serve as a benchmark on achievable performance. So in analogy of the information theory security, what we are trying to do here is we are minimizing an average cost, which tries to minimize the trace of the error covariance matrix at the remote estimator, but tries to maximize the trace of the eavesdropper error covariance matrix. So we weight these two costs by beta and -1 minus beta, because we are minimizing over the sequence of the scheduling decisions nu k. So now if we expand it out by as a function of the transmission scheduling decision and the packet arrival probabilities, then we can expand it like this. And beta is a parameter, the weighting parameter between 0 and 1, which controls the trade-off between the estimation performance at the remote estimator and the eavesdropper. So this is essentially a stochastic control problem. So whether you have a finite horizon scenario, where you are trying to optimize this cost over a finite horizon k, or if you have a long-term average infinite horizon scenario, in either case, you can use typical stochastic control techniques to solve these problems. So the problem can be solved using dynamic programming. I won't go into the details of this, but this is typical of any stochastic control problem. However, the difficulty with dynamic programming, as you all know, the curse of dimensionality. Note that the state here is the error covariance matrices in both the remote estimator and the eavesdropper. And they are actually takes value, in this particular case, in a countably infinite set. And I'll explain why that is the case in a moment. But basically, they stick, even though that's a discrete set, it's countably infinite. So in order to build a lookup table for this type of dynamic programming, you have the state dimension exploding, and therefore it's very difficult to implement it in a computationally efficient way. So we look at some structural properties of this optimal transmission scheduling. And as I said before, that when state estimates are transmitted, the error covariance of the remote estimator and the eavesdropper are totally ordered. So that means that if you receive a packet, you get your state estimation or eavesdropper error covariance to be p bar, which is the steady state error covariance at the transmitter. If you lose one packet, is f of p bar. If you lose two packets, is f square of p bar, etc. And this there is a total ordering relationship between these particular state variables. So this is my state space S, which is countably infinite. So what we can show, an interesting property of this optimal scheduling policy is it's a threshold type policy. So the threshold depends on the remote estimator error covariance and the eavesdropper error covariance. So if we fix the eavesdropper error covariance, then the scheduling policy is 0, the don't transmit when the remote estimator error covariance is below a certain threshold, and transmit if it exceeds that threshold. And similarly, if we fix the remote estimator error covariance, then the scheduling decision is 0 when the eavesdropper error covariance is above a certain threshold and 1 otherwise. Now, these thresholds here depend on their time varying, and but we'll see that we can show that in the infinite horizon case, when there is a stationary control policy, when new case star becomes a stationary policy, essentially the time dependence disappear. The thresholds become time invariant. So in the picture, what does it look like? So the two axes here are the error covariance of the remote estimator and the error covariance of the eavesdropper. And n is the number of packets lost towards the remote estimator, and the n is the number of consecutive packets lost towards the eavesdropper. So the blue shaded region is where your transmission is scheduled, and the white region is transmission is not scheduled. So basically, as you can see, as the remote estimator error covariance increases, you will have to, as more and more packets are lost, you will have to schedule a transmission, whereas it's the reverse for the eavesdropper error covariance. We won't go through the proofs, of course, but essentially the proofs depend on some monotonicity property of the value functions in the dynamic programming equation. Now I'll show an interesting result for the infinite horizon case. We know that for unstable systems, if the packet arrival probability at the remote estimator exceeds this threshold, where the sigma max is the largest eigenvalue of the A matrix, then the expected error covariance at the remote estimator can be kept bounded. But we can show that for any eavesdropper arrival probability lambda e that is strictly less than 1, there exist transmission policies in the infinite horizon situation such that the remote estimator error covariance is, on average, in the long term is bounded, whereas the corresponding quantity for the eavesdropper becomes unbounded. Similar results have been shown in some other papers, but they require, for example, large coding block lengths, or it required the eavesdropper packet arrival probability to be less than that of the remote estimator packet arrival probability, but we don't require such conditions. We can show this for any lambda e less than 1. And how do you do this? Basically, the mechanism works like this, that construct a policy with the required properties. Turns out that the threshold policy on P, when the threshold is sufficiently large, will work. Specifically, transmit if and only if the remote estimator error covariance exceeds this quantity f composition to the power t of P bar. That means if we have t consecutive packets lost in the remote estimator direction, you transmit, you schedule a transmission. Now, how do you choose t? Choose t such that this inequality is satisfied. So you can see that if you choose t large enough for any lambda e as arbitrarily close to 1, this inequality can still be satisfied, because sigma max a, this is for unstable systems, so sigma max a is actually greater than 1. Okay, so we can repeat this analysis now with removing the assumption that the eavesdropper error covariance is known at the remote estimator. So now if we assume that we don't know the eavesdropper error covariance PE at the remote estimator, then what can you do? We end up with a partially observed problem. So in that case, we can define a probability, a belief probability of the remote estimator, sorry, the eavesdropper error covariance being in these different states, given the previous scheduling decisions that we have made. Okay. So ideally, this state space is countably infinite, but for numerical purposes, you can truncate the state space at some point, some large value of k. So then this probability, the belief probability, has a recursive formula. When there is no scheduling, no transmission to be scheduled, it follows this recursive formula. And when nu k equal to 1, it has this particular recursive formula. So I won't go into the details of that, but basically you can write this conditional belief probability of observing a particular eavesdropper error covariance in this recursive form. So instead of knowing exactly what the eavesdropper error covariance is, now we have a conditional probability of that. So using this, you can rewrite the original cost function. Notice that before we knew the eavesdropper error covariance, now we don't know that, so basically we have a weighted average using these conditional probabilities. So again, you can use dynamic programming to solve this stochastic control problem. For both finite horizon and infinite horizon, you can use relative value iteration algorithms. You can obtain similar threshold type properties. So here the threshold depends on the conditional probabilities rather than the eavesdropper error covariance. And in the infinite horizon, you can prove similar properties. And in this case, the threshold policy constructed in the proof only depends on P and not, so the remote estimator error covariance and not the eavesdropper error covariance. So now we look at some numerical studies. And here we have a very simple two-state system and a scalar measurement systems. And we see that the packet arrival probability for the remote estimator and the eavesdropper are identical. So for a finite horizon case where the weighting parameter beta is 0.7, and you can see that if you choose the finite horizon as 4 or 6, you can see that the scheduling region is different because the thresholds are different when we have a finite horizon. Okay, so this tells you the scheduling region at k equal to 4, and this tells you the scheduling region at k equal to 6. So obviously, for a finite horizon scenario, finding the thresholds is a little bit difficult because it depends on the time index that you are considering. And for finite horizon k equal to 10, we compared the two scenarios where you have eavesdropper error covariance known and the eavesdropper error covariance unknown. So the property of the optimal solution in both cases. So the blue triangles represent the eavesdropper error covariance known, and the red triangles are the ones that the eavesdropper error covariance unknown. So we in the vertical axis, we have the trace of the eavesdropper error covariance, and the horizontal axis, you have the trace of the error covariance of the remote estimator. So obviously, we would like to make the eavesdropper error covariance very large and the remote estimator error covariance very small. So we'd like to be somewhere here. So we can see that when you know the eavesdropper error covariance for decision making, then we are in a better position because this blue curve lies above the red curve. And the reason why we haven't joined these points is because each of these points takes a long time to obtain using this the computationally. So we've simply left the points, marked the points instead of joining the points to make a curve. And then for the infinite horizon case, we show this exploding behavior of the eavesdropper error covariance. So this is an unstable system, and we take time average of simulation of length 1 million time steps, transmit if and only if the remote estimator error covariance is greater or equal to the composition of ft times. So that means t packets have been lost in the for the remote estimator. T consecutive packets have been lost. So in the first case, when we have both packet arrival probabilities to be the same, then we can see that as number of packets lost grows, the trace of the error covariance at the remote estimator also grows, but you can show that it will remain bounded because we have the packet arrival probability satisfying the threshold condition. Whereas for the eavesdropper, you can see that it is growing unbounded as more and more packets are lost. And the same scenario can be seen when the packet arrival probability at the eavesdropper is actually more than the packet arrival probability at the remote estimator. And in this case, again, you can see that the eavesdropper error probability, eavesdropper error covariance is increasing, not as at a high rate as in the previous case, but it's still increasing exponentially. And how to compute this threshold t? You simply look at the eavesdropper error packet arrival probability, and knowing lambda and sigma max A, you can show that the threshold needs to satisfy greater or equal to 2 when for the first scenario, and greater or equal to 3 for the second scenario. Okay, so now I'll quickly give another viewpoint of security, and this is more in line of information theoretic security. So here we talk about directed mutual information or conditional mutual information. So basically, we look towards the eavesdropper, and we want to restrict the amount of information revealed to the eavesdropper, in particular, the sum of conditional mutual information or directed information, which is essentially given by the mutual information between the state and the received signal at the eavesdropper, given all its past received signals. And very nicely, one can show that this can be written for this Kalman filtering example as this log determinant of the error covariance matrix, the prediction error covariance matrix, minus the log determinant of the filtered error covariance matrix. So if you don't receive a measurement, then your prediction and filtered remain the same, therefore you don't have any mutual information. Otherwise, you receive some information. So notice here that whenever we schedule a transmission, we're always leaking some information. And if you don't schedule any transmission, then you don't leak any information. So you have to strike a balance between the two. So here, the only difference with the previous scenario is that instead of maximizing the error covariance of the eavesdropper, we are trying to minimize the mutual information leaked to the eavesdropper. So we can come up with similar results, and I won't go through the details. The transmission scheduling problem in infinite horizon can be written in a similar way, and the problem has bounded cost because when you solve infinite horizon problems, you have to first show that the average cost remains bounded, and that holds when lambda, the packet arrival probability, is greater than this threshold, which is needed for the average error covariance of the remote estimator to be bounded. And in this case, we can show that no matter what transmission policy we'll design, no matter how secure you want to make, the average, long-term average of the expected mutual information leaked to the eavesdropper always remains bounded above 0. Okay, so unlike the case for where we're trying to maximize the error covariance at the eavesdropper, where we could make it grow unbounded on average, here we can see that on average we cannot make the mutual information go to 0. Okay, it will always remain above 0. So here is a pictorial illustration of that. A similar graph to the previous case where you saw the eavesdropper error covariance was growing unbounded, whereas here, as you can see, even when you make the average error covariance at the remote estimator quite large, you can still see that the average mutual information is somewhat, it's going decreasing, but it remains bounded above 0. However, this quantity epsilon is not easy to compute as such for any general scenario. So to conclude the talk, we talked about state estimation, privacy, or security in the presence of an eavesdropper, where the eavesdropper is trying to also construct an estimate of the state from the sensor transmissions. The transmit decisions, so here we look at a transmission scheduling problem. The transmit decision determined by formulating and solving an optimization problem, which is essentially a stochastic control problem. We, instead of just solving it by dynamic programming, we derive some structural results on the optimal transmission scheduling. And the structural results essentially show some threshold type behavior. In the finite horizon case, the threshold is not so easy to calculate because it depends on the time horizon. Whereas in infinite horizon, they become stationary, but it's not still, there is no closed form formula for computing these thresholds. And one of the interesting results is that the infinite horizon case for unstable system, we can make the eavesdropper error covariance unbounded while estimation error covariance remains bounded. We also looked at alternative notions of security, like using directed mutual information. One other thing I would like to mention is that the transmission of measurements instead of transmission of estimates. In this case, there is an interesting phenomenon that the structural results hold in the scalar case, but not for the vector case when you are transmitting a vector measurement. In that case, it doesn't generally hold. We have a counterexample for that. This work has now also been extended in multiple directions. You can show that if you go back to, this type of pictures, you can show that you can, in order to increase the error covariance at the eavesdropper, the error covariance at the remote estimator also increases, but you can show that you can do various other things, such as you can, let me go back to the very first picture. You can actually have multiple antennas at the sensor and the remote estimator, etc. And you can try to somehow control the information you release to the eavesdropper in a much more controlled fashion using multi-antenna techniques in signal processing and wireless communications theory. So there are other aspects of this type of privacy preservation that can be also looked at. And you can also extend the eavesdropper's capability from simply passive eavesdropping to also active eavesdropping, in the sense that they not only that they try to estimate the state, but they also try to jam the communication channel between the sensor and the remote estimator. And some of my other colleagues in Hong Kong, they have extended some of this work in these directions. So with that, I would like to thank you again for inviting me, and I would finish this talk. Thank you.
Great. Thank you, Subhrakanti. Thanks a lot. So the next session is actually the panel discussion. So we are running a little behind schedule. So whoever has questions, please ask. So we can probably take one or two questions.
Okay.
So in the meantime, I can probably ask one question, because I was curious about the case where you said A is unstable. So the eavesdropper covariance remains bounded when A is unstable. Like it will not go less than a certain value.
No, I mean, you can, that depends on the transmission scheduling policy. So for any, if there was no control of transmission scheduling at the sensor, then you can completely define the eavesdropper error covariance simply by looking at its packet arrival probability. And if the packet arrival probability is above a certain threshold, it will remain bounded. But if there is a transmission scheduling also going on at the sensor, that means sometimes the eavesdropper receives packets, sorry, it doesn't receive a packet when its channel is fine, the packet wasn't dropped, but there was nothing was transmitted, right? So by cleverly controlling this transmission policy, we can show that for any eavesdropper error probability, the error covariance at the eavesdropper can go unbounded. But that result only holds for unstable systems. For stable systems, you can show that both remote estimator error covariance and eavesdropper error covariance will always remain, on average, will remain bounded.
Okay. So there is a certain case scenario where when the system is unstable, then the covariance keeps on going unbounded.
On average, yes. So, I mean, obviously, if you think about packets being lost, then if you lose too many packets, their covariance will become very large. But then as soon as you receive a packet, it will come back to the steady state error covariance. It will go up and down, but the average behavior can be analyzed. So the first order moment can be analyzed and shown that this can go unbounded, provided the packet loss probability exceeds a certain threshold.
Okay. And how accurate are the models that you use for the network? So there could be errors in the model, right?
Yes. So you mean the knowing the packet loss probabilities?
Yeah.
So okay. So that's the only thing we assume about the network here. So the question is, of course, the packet loss probability for your own channel, the remote estimator channel, can be estimated over time and known if it's not changing with time. Right? Okay. If you have a fading channel, it may change with time. For the eavesdropper, that's a good question, that you may not always know exactly what lambda E is. But we can show that the lambda E, even if you have an upper bound estimate of it, so you can say that lambda E is less than something, and if you have that upper bound, you can still design a similar algorithm. The only thing we assume in this proof, which perhaps I didn't mention very carefully, or I skipped over it, is that the two channels between the remote estimator and the eavesdropper, those two lossy channels have to be mutually statistically independent. So, which means that if they are, of course, we know from antenna theory that if you have two wireless receivers, half of wavelength apart, the signals received there will be independent, right? Now we are talking about millimeter wave communications these days, so where the wavelength is much smaller. So even if you have an eavesdropper very close to the remote estimator, you can still satisfy this condition.
I see.
The independence between the two channels.
Okay, excellent. So I'm afraid in the interest of time, I will not be able to take questions from the audience. So with that, let's thank the speaker. Please press the clap icon below.
Thank you.
Okay, great. Yeah. So thanks a lot, Subhrakanti, for delivering the talk. So with that, we will end the session, and we will be having the COVID panel discussion, which is next. So we will be resuming in a few minutes. Okay, thank you.
Thank you.